see you all. And I'd to be outside here. The equality stream, if we're right next to the modem or whatever it's called. Hi, Lynn. Glad that this is working. So I'm going to be out here for just another second or two, and we can just kind of see. I was just disappointed with the quality of that stream. At times it was outstanding, and then as I think you all saw, there were other times where it just went to hell. And super fuzzy and warbled voice and skipping ahead and everything else. So that's the big experiment tonight. And yes, we're early. Still got about 10 minutes, so I'm going to walk inside with you in just a second, and I've got the chalkboard in there. Hello, Will. So I don't know what the weather's like where you are, but it could not be more perfect here in Ellensburg. And I certainly trust that things are good where you are. All right, well, I should get in there and walk with you here. It's the all night, unless the wind is up. This is a notoriously windy place in the spring, but we've had these magically calm evenings. There's plenty to worry about, so at least here we don't have to worry about the weather anytime soon. Oh, my slippers on here. All right. Ooh, it's kind of warm in here. All right, let's get set up here. See if we can frame this properly. And can I kind of zoom in like that? Hi, Bijou. Bijou the cat wants to say hi, I think. BFD, Brian F. Donaldson, nice to see you. Bijou, did you want to say hi to these guys? Let's say hi. Let's say hi to these guys. Yeah. So, Bijou and I would like to know, is the streaming any different so far tonight? Especially if I'm kind of planning on kind of being right here. Actually hoping the board would be a little bit more lit up. So if you wouldn't mind, in the next couple of minutes, especially if you watched last night, is this any better so far as the streaming quality? I'm mostly interested in the video the audio matching with the video. That was such a problem. Oh, I'm getting good reports. Much better, says J.A. A little quiet. Well, I'm not ramped up yet, you know. I don't have my Robotron voice going here yet. Oh, good. I'm not going to overthink it. I've seen enough good comments, and I guess because we're close to the wireless, whatever that thing's called, will be good. So, okay, Bijou, I'm putting you down. I might even come in a little far away. I agree. Can I do this? And if I do that, will my head be chopped off? That might do it. Perfect now. Okay. It's light. I guess that helps. Talk about amateur hour, my goodness sakes. That's the whole charm of this, I hope. still doing okay? We still warbled? Oh, I gotta. I'm not gonna be able to change the lighting at all. Froze. Oh my goodness. I'm gonna be about right here for most of this, and then I'm coming here. Okay. We got 5 minutes. I'm gonna go to the kitchen. I'll be right back. You stay put. I'm so glad that you're with us. Did you want to be let out, Bijou, before I start? Yeah, would you mind one more time? How we doing? Video stream, audio, syncing. We'd just love to hear from you one more time about that, and then I'll just ignore it. Perfect, good, great, okay. Robert, glass half empty. Sweet, wonderful. I won't think about it again. Don't know if I like, yeah, that'll do. Hey man, I don't want to have to step on you. Do you want to go out with Mom? I don't know if you should be in here. I think you're going out. You're gonna say goodbye to these guys, okay? You look right in there, and you say goodbye to these guys, and you're going outside, okay? Okay? You can go right out there. You had your nap. You're ready to go. Okay? All right. Good evening from Ellensburg, Washington. It's great to have you with us tonight. We are in the US of A, we're in the American West, we're in the Pacific Northwest, and I'm a geologist who specializes in this area. Once we leave the Pacific Northwest, my knowledge goes down for the most part. But I know this is more than just the Pacific Northwest on your end, so I'd be happy to answer some questions when we get there. What are the rules of tonight? Well, there are no rules. Number one, this is a homespun, home live stream, and we're all home these days, so why not try to do something together? What I have in mind is something similar to what I had last night, if you were with us. We talked about volcanoes last night, we're talking about earthquakes tonight, and we're talking about something called the Ice Age floods tomorrow night, March 19th at 6 p.m. Pacific time. I'm glad you found us. What I have in mind is, about 15 minutes of me talking about earthquakes, especially here in the Pacific Northwest. And I'm not even going to look at your questions or your comments until we're done with that. So if you could just hang on to those questions if you've got them about earthquakes, hang on till we're done with that. I'll let you know when we're kind of done with the program, quote unquote. And then I've got my laptop here on the sofa. I've got a chalkboard and I've got a whiteboard. I've got a couple of props. I'm not much of a prop guy, but we're going to use some props tonight. And hoping to help give you a few new ideas perhaps that you don't have already about earthquakes. And again, we have plenty of children joining us. Kids, thank you for joining us. I hope that you can stick with us and learn a few things as well. In fact, I'll start with some stuff that hopefully is for everybody, and then we'll move on a little bit. As opposed to last night where I had a bunch of brand new content that I was anxious to share, I don't have any brand new earthquake material. We can comment a little bit about Utah in a bit. But beyond that, I'm hoping if you've been a fan of things that I've been doing with the YouTube videos, etc., you've heard it all before. But I can tailor this to anybody who wants to ask. For just a moment, as I collect my thoughts, would you please type where you are viewing from? And we can feel some sort of sense of community just by having you check in. Where are you viewing us from? Terrible grammar. Hello, Mom. Glad you could join us again tonight. Okay, let's begin. Earthquakes. These are wooden blocks, and they are representing blocks of crust. And I like this as a way to visualize why earthquakes happen and how they happen, and how faults, some people not in science call it a fault line. It's not really a line. It's not really a fault line. It's a plane. It's a crack that has 3 dimensions to it. And we want to actually talk about these blocks as a starter. And then we'll go to the Pacific Northwest and talk about the fact that we have many earthquake issues here, not just one kind of earthquake. So, why does an earthquake happen? An earthquake happens when you have 2 blocks of crust that are the victims of stress. Now, we're all kind of on edge these days, so we're all kind of the victims of stress. But what I mean in this case is that if this is a place where we have a fault and we have the potential for earthquake activity on the fault, these 2 blocks of crust are not just sitting next to each other, they are receiving stress. And we can apply 2 different kinds of stress. I don't care if my head's chopped off here, we're just going to go for it. So I'm coming in here close. You're like, well, what is the HW and the FW? These are terms we have in geology. These are old mining terms, actually. If you're a gold miner, a silver miner, a copper miner, many times you're drilling a tunnel right on this boundary, right where this crack is. Can you imagine taking a power drill and just drilling right in along this crack and then having little cute little mining people, men and women, mostly men back in the day, but I suppose now it would be men and women of all different shapes and sizes and backgrounds who were in there walking around in this mining tunnel. The tunnel's on the boundary because faults typically are places where we have precious metals being deposited. But I'm getting off track. These terms, hanging wall and footwall, are terms for or labels for these two blocks of crust. That's important to us because here I go. I'm going to apply some stress to these two wooden blocks. You ready? I'm going to give you some audio now. I'm squeezing until finally there's so much stress pumped into these wooden blocks that we do this. There was a failure. Those blocks suddenly lurched past each other. And because I was squeezing these two blocks together, the hanging wall, which is the block of crust above the fault, got shoved up compared to the footwall, which is the block of rust below the block of crust below the fault. If I go back, if you're walking around in that tunnel that we talked about, you actually hang your lantern in the rock above the fault, and your feet are walking around on the footwall. So what's the rule? Big old earthquake, if we squeeze the crust for years and years and years, and we just don't back off, we just keep squeezing and squeezing until finally we break the rock along the fault plane, and we have an earthquake. So when you think of an earthquake, I want you to think of rocks breaking and blocks of crust suddenly lurching past each other. In the real world, this is a reverse fault. Crustal compression makes earthquakes on reverse faults. We're going to talk about reverse faults in the Pacific Northwest in just a second. The reverse faults here in Washington are a big concern for us. But is there another kind of earthquake with another kind of stress? The answer is yes. And this is what happened early this morning in Utah. You heard that there was a magnitude 5.7 earthquake just to the west of downtown Salt Lake City. There's some footage circulating around. It was scary. I haven't seen a report of a fatality yet. Thankfully, I haven't seen reports. What do I know? I'm just sitting at home, but I haven't seen anything that is beyond concern, but not loss of life or serious injury. And I hope that those reports continue for the Salt Lake City area. It's not only the big earthquake early this morning, magnitude 5.7, but there have been aftershocks all through the rest of today, perhaps even happening now. So what happened in Salt Lake City today? Was it what I just did? Was it a reverse fault that finally shifted? No, it was the opposite. It was a normal fault. There's something called the Wasatch Fault. If you've been to Salt Lake City, it's a flat basin and then a very steep mountain front and then the Wasatch Mountains. It's a beautiful area. But that steep transition from the mountains to that basin is the result of a normal fault. So we can also make earthquakes along normal faults. You ready? Instead of this compression and making a reverse fault earthquake because I'm pushing the hanging wall up, in this case, I'm going to try to do the opposite. It's not quite as dramatic. I'll give you some audio if you want, but it's hard to make it as dramatic. I don't know how this is going to work. So the opposite happened. What did I do with my hands? Instead of squeezing, I was actually relaxing my hands, crustal extension. So this is almost against our intuition to make an earthquake as I relax the crust. But that also is stress. And basically, stress and energy on that branch of the Wasatch Fault that ruptured this morning, there was enough stress pumped into that normal fault that finally we had a sudden earthquake by the hanging wall going down. Still a big earthquake, still disturbing to us, but not all earthquakes are the same. You can have earthquakes on normal faults, you can have earthquakes on reverse faults. And you can have earthquakes on a much bigger scale with something called a megathrust, which we'll talk about in a second as well. Okay, you probably have questions just on that, but again, I'm going another 10 minutes, wink, wink, by talking about the Pacific Northwest. I'm leaving Utah for now. You might want to ask about Utah in a bit, but I want to go to what I have on the whiteboard and the chalkboard, and I need to pick up the pace. I'm already 10 minutes in-ish, okay? So hopefully you can see what I have here. This is a plate tectonic cross-section of the Pacific Northwest. I'll let you look at it as I erase my schedule here. There's two tectonic plates here. Two different tectonic plates. So if one of your questions from just a second ago is why are we squeezing the crust or pulling the crust apart? The simple answer is it's all related to movements of tectonic plates. And in the case of Washington and here in the Pacific Northwest, it's a very obvious story because we have plates who are fighting. I don't know if you fight with your brothers or sisters. Hopefully the answer is no. Actually, we all fight with our brothers and sisters. That's real life. You're not supposed to be perfect, are you? So here's two tectonic plates. This is the ocean off the coast of Washington, Oregon, Northern California, and British Columbia. Vancouver Island. Shout out. This is called the Juan de Fuca Plate, and it is slowly but steadily subducting or diving beneath North America. This is a much thicker continental plate called the North American Plate. It's more than just the Pacific Northwest. This plate goes all the way over to Iceland in the middle of the Atlantic Ocean. It's a big plate. Well, a generation ago, in fact, when I started teaching in the early even in the late 1980s, we got too much sun now. We didn't really think that earthquakes were a problem here in the Pacific Northwest. But there's been some exciting research that's been done just in the last 30 years to completely transform the way we understand earthquakes. And it's bad news. We're not looking for bad news tonight, but it is bad news. We have much more concern about earthquakes here in the Pacific Northwest than we did 30 years ago. So what did we find? Well, it's like a three-ring circus. There's actually three very different ways that earthquakes are created or generated here in the Pacific Northwest. One way is we keep having you see those dots in that subducting plate? We keep having deep slab earthquakes, and we know very little about them. The Nisqually earthquake of 2001 that was underneath Seattle and Olympia, SeaTac area, that's the most recent time we had one of these deep slab quakes, magnitude 7.1 on the Richter scale. We also regularly, oh boy, have a bunch of shallow earthquakes as well. And those shallow earthquakes we know a little bit more about. The shallow earthquakes happen about as frequently, generally, as the deep slab quakes. A few of these events every century. The last big shallow crustal earthquake we had here in the Pacific Northwest happened in 1872. That's a long time ago. That's more than 100 years ago. The shallow crustal fault, we just found, by the way, north of Wenatchee, south of Chelan, just across the river from Orondo, if you happen to know Spencer Canyon. Geologists found that fault. It was a reverse fault, hanging while going up, that created that magnitude 7.4, that's the estimation of that earthquake in 1872. So we actually knew 30 years ago that we've had some shallow crustal earthquakes. There were some eyewitness accounts, there were some Native American legends, and we certainly knew there were some deep slab quakes. But the max for those earthquakes were, roughly 7.0, 7.4 on the Richter scale. By the way, each time you jump one whole number on the Richter scale, you increase the amount of energy released by a factor of 30. Magnitude 5, let's make that be one strand of uncooked spaghetti. If you want to YouTube something later, pasta quake. YouTube, put in the search box pasta quake, and Bob Butler does a very simple but beautiful illustration of how we increase by a factor of 30 the amount of energy released when we jump one whole number on the Richter scale. So magnitude 5, one strand of pasta. Magnitude 6, 30 strands of uncooked pasta. How much energy to break those? Magnitude 7 on the Richter scale, 30 times 30, 900 strands of, you get it? And so by the time we're up above magnitude 7 on the Richter scale, there is very daunting amounts of energy that are being released. Has that happened anywhere around the world? Yes. Has it happened on this map? I'm afraid so. That was the big discovery. We didn't realize these great earthquakes were even possible here in the Pacific Northwest. We now realize it's a thing. And it gets worse, I'm sorry. The biggest earthquakes, averaging magnitude 9 on the Richter scale. That's a lot of strands of uncooked pasta, thousands of strands. You can look at Bob's YouTube video to see it. It's happening underwater. It's happening out here at the oceanic trench. And as a result, there's a tsunami that's generated. You've heard of tsunami. Tsunami are the result of displacing a bunch of water in a hurry. And that's because there's a major disturbance on the bottom of the ocean, right at that oceanic trench. That's because we've got wooden blocks that are being released to all sorts of energy, way more energy than our shallow and our deep quakes. So the last thing I want to do, and again, this is just kind of a little getting a few things out there so that we can do some decent Q&A together, of all ages, I hope. Can I comment on why or what we know about the cause of each of these? We have some information now. We've been studying it for a while. Let's start with the one we know the least about. The deep slab quakes are happening regularly, and the surprise, where'd those wooden blocks go? The surprise is almost all of these deep slab quakes where we're actually breaking the crust 40, 50 miles below the surface are happening deep within the subducting plate, and they're normal faults. Normal faults within the Juan de Fuca plate are creating these deep slab quakes. Why are there normal faults down there? Which is really saying, why are we pulling the crust apart regularly at deep levels? Is that like what we were talking about last night, where we're actually breaking off a piece of the subducting plate? Nobody seems to know. But it's happening regularly enough in subduction zones around the world, these deep slab quakes, that there's some sort of phenomenon happening down there in all subduction zones that we don't fully understand yet. Let's leave that alone. Next one, shallow crustal quakes. These are these are shallower than 20 kilometers down. So just think 10 kilometers or less. And notice these are earthquakes happening within North America's crust, not at the boundary itself. There's a fault called the Seattle Fault, the Tacoma Fault, the South Whidbey Island Fault, the Saddle Mountains Fault, the Menashtash Ridge Fault, the Horse Heaven Hills Fault, the Toppenish Fault. And all of those shallow earthquakes are reverse fault earthquakes. That's the payoff for knowing, remember this one? Boom! The question is, well, two questions. How often do these faults make reverse fault earthquakes? I can give you a basic answer. Every few thousand years. Maybe every 10,000 years. Maybe every 20,000 years. You're like, what's the answer? We don't know. We don't have enough information on each of these faults. And information, I mean, we don't have enough past earthquakes recorded on those faults to know the average number of years between events. But what we do have a decent feel is why those shallow crustal faults keep happening. The 1872 earthquake I talked about north of Wenatchee. All of these shallow crustal faults in the Pacific Northwest. Again, this is a thank you to Bob Butler. So here's the answer, as we understand it currently here in 2020, for why we're having shallow crustal earthquakes in Washington regularly. By the way, we're not having shallow crustal earthquakes regularly in Oregon or Northern California, but we're having them here in Washington. We're having them here in Ellensburg. Every few thousand years, not every day. I'll make it quick. Have you seen this before? This looks like it's going to be really fun. It's kind of disappointing, I must say. This is the whole thing. Doink, doink, doink. What am I doing? I'm showing you that we have instruments now to measure precise movements within the Pacific Northwest's crust. And we know that Northern California, Western Oregon, and Western Washington are slowly moving north. I'll do it in slow motion, without a glare on your screen, hopefully. You see what I'm doing? I'm taking Northern California, the Sierra Nevada block, and I'm pushing it up against the Coast Ranges blocks, and I'm causing this crust within the Pacific Northwest to clockwise rotate, to rotate clockwise against British Columbia and Northern Washington, which is not doing any rotating. So we're squeezing the crust. I don't know, can you see? I can do it this way for you. We're forming ridges. You saw the ridge at the beginning of this live stream, I think. That ridge is there because of this clockwise rotation. And instead of just a gradual folding to form these ridges in central Washington, we're also having faulting. Did I just say faulting twice? There's folding and faulting in something called the Yakima Fold and Thrust Belt that we're very concerned about. The concern is we know that earthquakes are an issue, but they don't happen frequently enough for us to know the odds of when a magnitude 7 earthquake will happen on one of those shallow crustal faults. So the shallow guys are happening within Washington, and it is reverse every time. Squeezing Northern California, getting closer and closer to Canada every year. We get these every once in a while. The Seattle Fault made an earthquake like this, where everything south of the Seattle Fault went 21 feet up compared to the north side of the Seattle Fault. And we have all sorts of evidence for that we can talk about if you like. We're saving the worst for last. I'm sorry. We're saving the worst for last. The trench-related quakes. I'm going to try to do this on the chalkboard very quickly because we're almost 30 minutes into this again. Like, this guy's losing his mind. He's got it right there. Why didn't he do it there? I want to do it here. Get off my back, all right? I want to do this the way I want to do it. Just kidding. Here's our current understanding of why we have great earthquakes, magnitude 9 earthquakes regularly with our subduction zone here in the Pacific Northwest. we're sure that the Juan de Fuca plate is actively subducting. But we also have a lot of evidence to suggest that the boundary between the subducting ocean plate and the overriding continental plate is stuck. It's locked. In other words, there's no slippage as this ocean plate continues to slide beneath North America. And so as a result, if this is locked, if this boundary is locked, and this ocean plate continues to slowly subduct beneath Washington, Oregon, and Northern California, and British Columbia, then we're going to take the leading edge of the North American plate, and you see what I'm doing? I'm pulling down I'm just going to say Washington for simplicity. I'm pulling down the edge of Washington with the subducted plate. It's a locked boundary, and this is what's going on. Should I put the ocean in? That dot is Westport, Washington, or Ocean Shores, Washington. Any coastal community in the Pacific Northwest. You got to be truly at the ocean now, not Puget Sound. The ocean. So we're taking this crust, and out at the trench, out at the boundary, we're dragging the edge of North America down with the subducting plate. Because it's a rigid thing, do I have something that's rigid? Don't do it. Don't say it. I don't want to break it. Poor planning, sorry. I don't have anything. If I'm going to put the edge of this book down, that means at the same time I'm going to be gradually arching the crust at the coast. Let me say that again. If at the lock zone I continue to pull the edge of Washington down, simultaneously I'm arching the crust at the coast. But we all know this can't go on forever. And I'll cut to the chase. With our current understanding and our current field data from the coast and also offshore in submarine canyons, in Washington, we now think there's a 500-year cycle. A 500-year cycle of pulling the edge of Washington down in the trench, pulling the edge of it down, 500 years of pulling it down, in other words, 500 years of arching it up at the coast until the lock zone becomes unlocked. And we restore the book. We restore the crust. We have a massive amount of movement. This is the mega thrust fault I was talking about. This is a reverse fault, much, much bigger scale than the wooden blocks. And by taking the edge of Washington underwater and suddenly having the crust move tens of meters at the snap of a finger, that means we're suddenly going to drop the crust at the coast. That means we're going to suddenly displace a bunch of water, and we have a bad situation with ground shaking, magnitude 9, regionally, and tsunami waves crashing at the coast. This sounds like science fiction, but it happened in Japan in 2011. It happened in Sumatra in 2004. It happened in Chile in 1960. It happened in Alaska in 1964. We don't need to dwell on this. We've got enough issues going on this week. But if we want to understand earthquakes here in the Pacific Northwest, unbelievably, it's all three of these things. And so if God forbid the ground, my house started to shake right now during this live stream, I really wouldn't know if it was, I wouldn't know, is it shallow, is it deep, is it trench? Wouldn't know for a while. And we're far enough here in Ellensburg, we're far enough east of the trench that tsunami are not a concern here, but we would definitely feel the ground shaking. Okay, it's 6:30. That's plenty. Yeah. I think we'll just stick right here and see if I want to use some of this stuff. Thank you for your attention. I don't know if you were paying attention or not. Thank you for your attention during the lecture. And now let's go ahead and answer some questions. And I know how to scroll now, finally, on my laptop. If you weren't with us last night, I would ask for some uppercase caps lock for your questions. I'll be able to see them easier. God, I still don't know how I want to do this best. Okay, what's the evidence for 500-year cycles? Tsunami deposits, question mark? Okay, these are all good questions. I won't say that every time. They're all good questions, I'm sure. Okay, how do we know 500 years? It's really crazy, wonderful work. At the coast, we have tsunami deposits. So, even more accurately than that, if you go to some swamps or some coastal lagoons, some estuaries, Brian Atwater is the very famous geologist who did this, you can find evidence for sudden land level change, oftentimes associated with a tsunami. And so there's a way to tell that the ground suddenly dropped. In other words, you have plants that were growing above a tidal zone, and then suddenly the land suddenly dropped 6 feet, let's say, and the roots of those trees are now plunged into salt water and they die. And using tree ring evidence and some carbon dating of some organic material, other things that don't come to mind at the moment, 500 years, that's where that number comes from. I must include that there is perhaps in Oregon, so with these great earthquakes, gosh, I shouldn't have picked this spot. So we're talking about, here's the trench offshore of the Pacific Northwest. I'm not doing the crustal thing now, I'm doing the deep slab, I'm doing the great earthquakes. Oregon, some of the offshore underwater evidence is starting to tell us that there's a potential for more great earthquakes. It's not an average of 500 years between great earthquakes in Oregon. It's perhaps more frequent. And there's growing evidence that not all the great earthquakes are magnitude 9. You could have a magnitude 8 or a magnitude 8.5. So I'm hesitating because I don't want to say something incorrect. I'm also hesitating because there's still data that we're trying to work with that even connects some of this to the San Andreas Fault. That's the newest work by Chris Goldfinger. Let's move on. I don't like this lighting here. Let's try this. Okay, I got you now. How far inland would tsunami reach? Fair question. I need a map. Okay, I'm going back to this. Sorry, did you get seasick? We're going to be here all night, I think. This is almost impossible to do in just a few minutes. Let's do this. Oh God, yeah. I'm gonna get the Canadians in there. Okay, so if we're talking about tsunami, people are concerned now, like, oh wow, is the tsunami going to come to my house? Well, let me try to give you some good news first of all. The tsunami inundation zone, this is Washington, Oregon, and California. Here is our trench, about 55 miles offshore, underwater. That's where the lock zone is becoming unlocked. The tsunami inundation zone is the width of that yellow line. Does that make you feel better? That We don't have all of Washington and Oregon being overrun by a tsunami. We don't have tsunami at Ellensburg or Yakima or Bend. We don't have tsunami crossing the Cascades. There's no evidence for that, and those are very simple and safe statements to make. But this is something called the Strait of Juan de Fuca, where tsunami now have been modeled to come through. So we unlocked the lock zone, and we're now understanding that there are tsunami from the Pacific Ocean that can get through the Strait of Juan de Fuca and enter Puget Sound. And there are new studies being done where we're looking for tsunami deposits in Puget Lowland, Puget Sound, Whidbey Island, etc., and trying to figure out which tsunami deposit is from which earthquake. Are they all coming from the trench, or are some of them shallow crustal earthquakes? But the point is, we're starting to get some evidence that tsunami can get into Puget Sound country. Let's keep it going. No, come on now, let's not go too far with these comments. I'm going to scroll. I'm going to pick. I'm in charge. Alexander Haig, if you know that. Yeah, I'm asking for uppercase. I'm not seeing much uppercase. I can't easily read your questions otherwise. Wouldn't a reverse fault also be considered a subducting or subductive fault? Yeah, this is commonly called a megathrust. And a thrust fault and a reverse fault are basically the same thing. The difference is a thrust fault has a shallower angle, reverse fault has a steeper angle. But both faults are from squeezing, and the other difference is this is squeezing on a huge scale between two major plates because of our lock zone situation. The reverse faults are very small cracks that don't have the size of our megathrust. I'll keep it going. Thank you for being with us. I have no idea how many we have here tonight, but I'm going to scroll back and try to find where you maybe went nuts with your questions. Why would the Juan de Fuca roll back in a break and rebound? Seems likely it would become structurally unloaded and rebound. Well, Scott, that's our model that explains best our evidence for this cycle. At the coast, we have 500 years of uplift and then a sudden drop, and then 500 years of gradual uplift and then a drop. I'm not quick enough to get the impact of your question, sorry. When was the last megathrust? Sure, that's an easy one. The entire trench unlocked. Again, we're starting to see that sometimes we can get a trench quake, but it's not the entire trench that unlocks, it's just a portion. But on the evening of January 26th, the year 1700, at 9 o'clock Pacific time, the entire trench from Vancouver Island down to Cape Mendocino unlocked. It was a full rip, as we call it. And we know that because we have tsunami evidence along that entire margin. And I don't even have to look. I know the question now is coming, how do you know that date? And how do you even know the time of night? And that again is this fellow Brian Atwater, who said, well, wait a minute, we've got evidence for this tremendous great earthquake, magnitude 9-ish, here along the coast of the Pacific Northwest. Don't tsunami travel across the Pacific Ocean? If we had tsunami, big tsunami waves crashing on our shore, shouldn't there be big tsunami waves from our earthquake also arriving in Japan hours later? So he went over to Japan. They have wonderful written records going back centuries. He found, with the help of village historians in Japan, the precise day and time of day that an orphan tsunami arrived in Japan and damaged coastal communities, killed people in Japan from our unlocking event. And he back calculated, knowing the travel time of his tsunami going across the ocean, to figure out January 26, 1700, 9 o'clock local time. Amazing stuff. It's not every 500 years before that, but it's an average of 500 years. Okay, thank you. Let's keep them coming. Issaquah, right, along the I-90 corridor. Yes, the Seattle Fault. Now we're going back to our shallow crustal events. See, it's so difficult for us to keep these things straight. The Seattle Fault made news 30 years ago. Actually, when we first moved to Ellensburg, everybody was reading newspapers at the time. Seattle Fault discovered. And it's like, wow, really? There's a big, brand newly discovered fault, a reverse fault that basically goes right along I-90? Yes. So, Washingtonians, if you know the drive from, I'm sure you do, Seattle, Issaquah, North Bend, you're heading basically from Seattle east. What do you have on your right? You've got a big ridge, the Issaquah Alps. What do you have on your left? Lower country. There's some glacial signatures there, but basically I-90 is driving right along the Seattle Fault, and everything south of the Seattle Fault has lifted each time we have an event on the Seattle Fault. And you can repeat that for the Tacoma Fault or all these other shallow crustal reverse faults in central Washington. But those aren't magnitude 9. Again, we got to keep our things straight. The shallow and deep events they appear to top out at magnitude 7, 7.5 maybe at the max, not the magnitude 9. I'm getting sad talking about this stuff because we're already not feeling so good these days, just generally. So it's often different giving this lecture in different times when we're feeling a little bit more secure. So hopefully we're celebrating the science and how much we have learned in the last few years and all these dedicated research people doing this amazing scientific work. And if you just think about it, if we've learned that much in 30 years, think of how much more we'll know in 30 years from now. There's reason for hope that we will continue to learn more and more about these things. So let's choose to view it that way. Can normal fault like the Wasatch Fault have slow slip events? No, not to my knowledge. Let's do that very quick. I think I'll just do it verbally. I'll do it like this. This is really one of the biggest mysteries we still have with the earthquakes in the Pacific Northwest. Really fighting the lighting. Maybe it's much better from your end. I feel like I'm struggling with lights here tonight. Okay, so remember what we did? Shallow crustal events, remember? Reverse faults, only in Washington. We don't have shallow crustal earthquakes. We don't have shallow crustal earthquakes in Oregon typically and Northern California because they are within these rotating blocks. By comparison, Central Washington and Puget Sound has lots of these active shallow crustal faults because we're kind of in this crunch zone between everybody rotating around clockwise, Pendleton, and Canada. What's the question? Yeah, slow slip events. So there's this amazingly mysterious thing that we really don't understand. I don't want to do it here. I'll just do it verbally. Nope, I'll do it here. Every dot is a GPS station. It's like a little tripod with a permanent receiver drilled into the bedrock, and that little GPS receiver, it's actually bigger than my head, is communicating with satellites in space. We can get very precise locations of each of those GPS stations. So as you would expect, each day, each hour, actually each half a second, we have data from all these receivers pouring into the geology building a few blocks away from here at Central Washington University. And we process that GPS data. Here's what a slow slip event is. Every 14 months, a few dozen of these stations stop rotating. and they actually start creeping back for 2 weeks. And then they start rotating again. And then another cluster of GPS receivers show this gradual rotation in a clockwise sense. They stop for 2 weeks. They just, for a fraction of an inch, go backwards, and then they go again. There's energy being released, but over a 2-week period. So there are earthquakes that happen that none of us feel, but instruments pick up that slow slip energy. Episodic tremor and slip, ETS events, they're called more formally. Now, is this related to our clockwise rotation? Are these ETS events, these slow slip events, more tied to the subducting interface? And is something happening within our locked zone? It's more along those lines, but there's this transition zone deeper than the lock zone that appears to be doing this kind of funky thing every 14 months. Big mystery. Cody Molyneux. I recognize you. I see you. My heart is open to you. Thank you for being here. I love you, Cody. Can earthquakes trigger volcanoes? It's a common question. Like this great earthquake thing, the next time it happens, the next time we unlock the lock zone, are we not only going to have that huge earthquake and a big tsunami, but are we going to kick off an eruption of one of our Cascade volcanoes, let's say? It's a common question, I get it all the time. My answer is, we can't rule it out, but we have no evidence for that. Can't rule it out. I can't say no. But I can't say yes because we have no evidence of a big volcanic event that matches perfectly to the year that we have on some of these earthquakes, either in the trench or the shallow crustal events, or even the deep ones for that matter. Now, we could be pessimistic about it. Let's just do that for a second. We don't have much information. We don't have enough of these prehistoric eruptions. We don't have enough prehistoric eruptions recorded geologically, written down. We don't have enough past prehistoric earthquakes. In other words, we just don't have inventory. Maybe at some point we'll get to the point where each fault that we know in the Pacific Northwest that's active, we can give a date for the last 10 events and do all sorts of statistics to say, here are the odds of what's happening in the future. And if we have that inventory on these earthquakes, on known faults, active faults, and we're up in the Cascades like last night's talk, and we're getting dates on lahars and other major events with volcanoes, then we could eventually say this is a thing. But we have no evidence to suggest that we're going to trigger something else. Can strike-slip faults trigger a tsunami? Not to my knowledge. Most of us know that strike-slip faults, we're back to where we started with our blocks. A strike-slip fault is where, I'm going to do audio again for you. That's a strike-slip fault. It's sudden lurching of these two crustal blocks, but the lurching is happening horizontally instead of vertically. And so the question was, well, first of all, to get a tsunami, we need to have this lurching of crustal blocks underneath ocean water. And our reverse faults are making tsunami. Normal faults we make tsunami because we have vertical motions. I know of no evidence of a strike slip event, let's say off the coast of Cape Mendocino near the Triple Junction, generating a tsunami? I think that's a pretty safe no. Good question. I mean, thank you for the question. They're all good. Full rip question mark, is that the ghost forest? Well, full rip is a phrase more than a technical thing. There's a book called Full Rip 9.0 written by Sandy Doughton, who writes for the Seattle Times. It's an excellent book. So the full rip is referring to the next time we unlock our locked zone, is it going to be a complete unzipping of the trench or a partial unzipping of the trench? And the general rule is the longer the fault rupture, the bigger the magnitude. The ghost forest is one of these places at the coast where we had a bunch of trees die in 1700 because of the roots being plunged into the salt water. So there's a connection between full rip and ghost forest, but two different things, two different places. Mind blown, more of a comment really than a question. What are the theories for explaining the deep slab quakes? I don't really know. I shared with you what we do know, and that we keep having these earthquakes deep within a subduction zone. I think you're asking what are the potential ideas of what's going on down there. I guess one thing comes to mind, that perhaps we are taking a rigid subducted plate that's deep and we are bending it. Again, I don't have anything rigid, but if you take something rigid and you bend it, you're cracking the upper surface and you're compressing the lower surface. So maybe this is from a flexure of the subducting plate, but that's not very satisfying. An explanation of the New Madrid earthquake. No, I don't have one. The biggest earthquake in U.S. history. In other words, the biggest earthquake recorded in our country's history since 1776 happened in 1811, 1812 in New Madrid, Missouri. Three big earthquakes. That's a long way from a plate boundary. I don't live back there, so I haven't kept up on the latest, but I think I would have heard of something if there was a major breakthrough in our understanding of that. I'm sorry, I don't have anything intelligent to say about that. Do we have evidence of a tsunami in the Columbia River? I think what you're asking is, when we unlock the lock zone, especially if we're unlocking the lock zone offshore of where the Columbia River is entering the ocean, at Astoria, Oregon, let's say, or Ilwaco, Washington, how far up the lower Columbia can we find tsunami deposits? I don't really know. I think there are some tsunami deposits that have been found. This is a relatively recent thing. I can't stress enough, this is not a cop-out. I partly just don't know, because I'm not up on the latest down there. But this is also, Brian Atwater was finding these tsunami sediments for the first time in 1986. It's not that long ago. And there's just a handful of geologists who are excellent, and this is their specialization, but there's just a handful of people with a few students that are working with them. And so we just have to hopefully keep funding this kind of work to find more and more of these tsunami deposits and get this inventory that I keep talking about. So is it possible a tsunami from the ocean would come up the Columbia as far as Portland? That seems reasonable to me, but I'm confessing I don't know exactly how far east a tsunami deposit has been found up the Columbia River. Does Hawaii have earthquakes as well as volcanoes? Absolutely. There have been some amazing discoveries in the last 30 years, let's say, out there as well. One big discovery is that if you look at a bathymetric map, In other words, the landforms in Hawaii under the water. So can you just picture, I've got this chalkboard. Why aren't I using the chalkboard? So let's just pick the big island of Hawaii and Maui, let's say, okay? And so this is the island, this is the island, and the rest of this is water. Well, there were some amazing maps that came out, I'm not sure exactly, let's say 30 years ago, I'm not totally sure. I'm drawing turtles, sea turtles now. These amazing maps came up and showed these amazing mounds of material that were sitting underwater on all flanks of these islands. And those were studied very carefully, these big land masses underwater off the coast of Hawaiian Islands. And it was concluded those were huge landslides. In other words, you have, especially because of the volcanic activity, there's something called the East Rift of the Big Island, for instance, where there's been some active magma coming up. There's another big crack to the southwest. And the main point is that eventually you inject so much magma into that portion of the island that a portion of the island starts to move away from the rest of the island until there's a catastrophic landslide of that material falling into the ocean. There's earthquakes associated with the injecting of magma. There's also earthquakes and even tsunami associated with land masses falling off into the continental slope. I see kid question, but I don't see the question. I'm sorry. Would it be safe to say there's an earthquake every day in Washington? Would it be safe to say there's an earthquake every day in Washington? Yeah, probably. There's a couple of wonderful websites that I don't go to as often as I should. USGS comes to mind, but I'm sure there's some better ones as well. Pacific Northwest Seismic Network, or I'm embarrassed to say I don't remember right off the top of my head, but there's an active real-time catalog of earthquakes big and small. And yes, every day there's many earthquakes that we don't feel, but they're happening. And if you're a kid doing a report and you want to report on how many earthquakes there were last Tuesday in Washington, you can find that information. And you're an intelligent scientific crowd. That's, I hope, that why you're here. And we know that all the information that these agencies have, they are sharing with the public. That's their role. We'll do a couple more and then we'll quit. It's almost 7 o'clock. We're going to stop with this one, actually. It's a good one. The question is, do we know why this rotation is stopping in northern Washington and Canada? And that is also a common question, an important question. Remember now, this is talking about our shallow crustal events. And as long as this clockwise rotation continues, we're going to continue to have shallow earthquakes in Washington. The question is, why isn't everything rotating? Why isn't this stuff rotating up here? Don't totally know. Again, we made the rotation discovery about 20 years ago. How do we know, first of all, it's not rotating up there? Well, you remember those GPS stations? We have sea turtles now. Those GPS stations are not rotating north of Wenatchee, basically, all through the Okanagan, up into BC. They're not doing anything. They're not part of this rotation story. And so therefore, we're not squeezing the crust like we started. The best answer at the moment to explain why we don't continue to have that is the size, I should do it, is the size of the two ocean plates that are offshore. So this is a nice way to end. It actually ties right back into what we were doing last night. Pacific Northwest. Actually, I was intending on doing this last time I drew this, and then I kind of got distracted. Imagine that. All right. The basic message is we think that this clockwise rotation is happening because of the movement of the two ocean plates offshore. And that if we get far enough inland or far enough north away from these active ocean plates, we lose the ability to rotate. So one way to say that is, this is the Pacific plate that's moving great guns. It's got a high velocity. It's moving fast every year. And it's grabbing a hold. I mean, here's a whole nother stuck boundary. That's the San Andreas Fault. Totally different kind of a story than tonight. But you can just think of Northern California being sent northward because this Pacific plate is locking, almost like a dog's grabbing a hold of your shin and not letting go. And the dog's continuing to go this way and grabbing your pant leg with you. I don't know if that works or not. And this is a different tectonic plate, the Juan de Fuca plate, the one that's subducting beneath us here in the Pacific Northwest. But it has kind of a northwesterly trend. And so the Pacific plate doing this, the Juan de Fuca plate doing this, is grabbing a hold of basically that area and rotating it. And by the time we get up north of the chalkboard, we don't have an ocean plate offshore that has that kind of a vector to it. Okay, it's after 7 o'clock. I have one thing I want to show you. I was distracted earlier on because a former student of mine that sat in the whole quarter was going to bring over a gift. And I think it might be a gift for all of us. His name is Jeff. So let me see if I can find this thing and bring it in. I have a hint as to what it is. Can I get a knife? So I have my geology class open to the public, and we have a lot of townies that come and just take it for free. And sometimes they feel like they want to say thanks in a unique way. So there's a new bakery in town, Heyday Bakery, I think. This episode brought to you by Heyday Bakery. This is a knife, and this is a German chocolate cake. Not related to tonight's talk. But last night we were talking about flood basalts in eastern Washington. We talked about them briefly. David Walter kept asking yesterday about why those flood basalts are so thick and so uniform in their thickness across such an amazing area of the Pacific Northwest. All I can say, David, is those flood basalts had so much volume that we could maintain that thickness over such a large area. Can I do this? And so there's 3 miles of this basaltic lava that has flooded much of the inland Pacific Northwest. And my analogy, is a German chocolate cake. Oh my God, oh my God. And there's some sedimentary horizons between those basalt flows that represent quiet times, thousands of years of quiet time between the basaltic eruptions. That's a German chocolate cake. So Jeff, Steve, Cooper the dog, Sharon, Glenn, Merle, and a few others I don't remember, the townies from this group that just finished. Thank you for this German chocolate cake, this basaltic pile of lavas. There's another one of these in Siberia. There's another one of these in India. And here's our toast for tonight. Last night was a St. Patrick's Day toast. Here's the toast for you for joining us tonight. Hope that you're well. Hope your parents are well, your grandparents are well, your friends are well, your pets are well, your insects are well, your vegetables are well, and your German chocolate cakes are well. Thanks for joining us tonight. We'll see you tomorrow night. Ice Age floods, 6 o'clock. Don't miss it. I love you. Good night.